Right now, somewhere in the Milky Way, there could be a civilization 1 million years older than us. Older than us the way we're older than bacteria. They could have solved cancer, aging, poverty, war, everything we're still stuck on. They could have technology so far beyond ours that to them, a smartphone would look like a sharpened rock. And yet, according to the math I'm about to show you, that civilization is almost certainly still trapped, stuck on their home planet or at best, crawling around a handful of nearby stars. Not because they're not smart enough, not because they don't want to leave, because the universe itself is built like a prison, and the walls of that prison aren't made of steel or stone, they're made of physics. Rules that apply to them exactly as much as they apply to us. Rules that no amount of intelligence, no amount of time, and no amount of money can bend. By the end of this video, you're going to understand why the night sky is silent. Not because we're alone, but because getting from here to anywhere might be one of the hardest problems in the entire universe. Harder than curing death, harder than building a Dyson sphere. Maybe even harder than reversing entropy itself. Let's break down exactly why. Everyone's heard that space is big, but big is a word we use for a football stadium. It's the wrong word entirely for what we're dealing with. Let's use a trick to actually feel it instead of just hearing the number. Shrink the sun down to the size of a basketball. On that scale, Earth is a grain of sand orbiting about 26 meters away, roughly the length of a bowling lane. Neptune, the edge of our planetary neighborhood, is almost a kilometer out. Now here's the part that breaks people's brains. On that exact same scale, basketball sun, sand grain Earth, the nearest star to us, Alpha Centauri, would be over 6,700 kilometers away. That's the distance from New York to London, and most of the way back. And Alpha Centauri isn't far by galactic standards. It's our next-door neighbor. Our galaxy contains over 100 billion stars, spread across a disk 100,000 light-years wide. If our solar system were the size of a coffee cup, the Milky Way would be the size of the continental United States. And the Milky Way is just one galaxy. There are an estimated 2 trillion others. This is the first thing to understand before we even talk about physics. The distances involved aren't just far, they're a different category of far. The kind of far where our intuition simply stops working, because nothing in human experience has ever prepared us for numbers like this. Now, let's talk about why those distances might be permanent. Here's a question worth sitting with. Why can't we just build a faster engine? We built engines that go from horse-drawn carts to jet planes in about a century. Why would speed ever stop scaling? Because past a certain point, you're not fighting engineering anymore. You're fighting the actual geometry of the universe. Einstein figured this out in 1905, and the core idea is stranger than most people realize. Space and time aren't two separate things, they're one combined fabric, space-time, and every object in the universe is always moving through that fabric at a fixed total rate. Right now, you're sitting still in space, which means you're moving through time as fast as anything can possibly move. The moment you start moving through space, some of that motion budget gets redirected. You slow down through time to speed up through space. This isn't a theory, it's been measured directly. GPS satellites have to correct for it every single day, because their clocks genuinely run at a different rate than clocks on Earth. Push this to the extreme. At 90% the speed of light, your onboard clock runs at less than half speed compared to home. At 99.9%, it's over 22 times slower. And to actually hit light speed, your clock would have to stop completely, meaning you could never take another step forward, because forward motion requires time to pass. There's a second way to see the same wall. As an object speeds up, it effectively gets heavier, harder to push. Not because more atoms appear, but because energy itself has mass, and speeding up requires pumping in energy. At normal speeds, this effect is too tiny to notice. But as you approach light speed, this effective mass rockets toward infinity, which means the energy needed to nudge you even faster also rockets toward infinity. You would need an infinite amount of energy to reach the speed of light. Infinite. Not a lot. Not more than we have. An amount that literally does not exist. That's why photons, particles of light, can hit that speed. They're the one thing in the universe with zero mass, so this rule doesn't apply to them. Everything else, including a spacecraft made of the lightest materials imaginable, is locked out forever. So step 1 of the trap. No matter how advanced you get, you cannot outrun light. And light itself needs over 4 years just to reach our closest neighboring star. Okay, you can't beat light speed. Fine. What if you get close? Say, 90% of it? Let's actually price that out. To push a spacecraft the size of a small car, call it 1,500 kilograms, up to 90% of light speed, you'd need something in the neighborhood of 10 to the 20th joules of energy. To put that in a number you can hold on to, that's roughly equal to the entire planet's electricity generation for an entire year, just to launch one vehicle the size of a Honda Civic. And that's before you account for the fact that you also have to slow down on arrival, or you just scream past your destination at nearly light speed and keep going forever. So double the fuel requirement, roughly, except it's worse than double, because the fuel you need to decelerate has to be carried and accelerated along with the ship for the entire outbound trip. That extra fuel has mass. That mass needs its own fuel to accelerate, which needs its own fuel. This spiral is called the tyranny of the rocket equation, and it's brutal. It's the reason a real spacecraft aiming for relativistic speed doesn't need double the fuel. It can need hundreds or thousands of times the payload mass in propellant alone. What kind of fuel could even theoretically deliver that much energy density? Chemical rockets are laughably insufficient, they're not even in the conversation. Nuclear fission gets closer but falls far short. Fusion, which humanity hasn't even mastered for power generation yet, still isn't dense enough on its own. The only fuel physics allows that's dense enough is matter-antimatter annihilation, the most efficient reaction the universe permits, converting 100% of mass directly into energy. But we've never produced more than a few billionths of a gram of antimatter in all of human history, at a cost of billions of dollars per nanogram. You'd need tons of it, tons, stored in perfect magnetic containment, because a single leak means it touches ordinary matter and detonates like a nuclear bomb. Now scale this up to something that could actually carry a crew, food, water, radiation shielding, life support, not a civic-sized probe, but a real ship. The energy curve doesn't just go up, it goes vertical. We're talking about energy requirements that could exceed what a civilization can extract from its entire home star system. This is the part people miss when they say, a sufficiently advanced civilization could just build a better engine. Better engines still answer to the same energy equation. You can improve efficiency. You cannot cheat conservation of energy. Let's say hypothetically a civilization somehow does crack the antimatter problem. They accelerate to 95% of light speed. What happens next isn't triumphant. It's lonely, in a very specific way. Because of time dilation, the crew might experience a journey to a nearby star as only a decade or so. But back home, 13 or 14 years have passed. Their families have aged. Their government might not exist anymore. If they're gone for a round trip across a meaningful stretch of the galaxy, they're not visiting the future. They're permanently emigrating into it. There's no calling home for advice mid-mission either. A radio message takes years each direction, so any emergency has to be solved entirely alone, by whoever's on board, with whatever they packed. And a mission across the whole galaxy, 100,000 light-years, doesn't compress into a human lifetime, no matter how close to light speed you get. Even with extreme time dilation, you're talking about tens of thousands of years experienced on board. That's not a spaceship mission anymore. That's a sealed, self-sufficient civilization that has to reproduce, govern itself, and keep its life support systems running without failure for longer than agriculture has existed on Earth. We have never built a machine that runs flawlessly for even 100 years unattended, let alone 10,000. There's a detail that rarely makes it into the popular version of this conversation. Interstellar space genuinely does contain matter. It's incredibly sparse, roughly 1 atom per cubic centimeter on average. But sparse stops mattering once you're moving at relativistic speed. Kinetic energy scales with velocity squared. At 90% plus of light speed, even a single dust grain becomes a serious weapon. A particle with the mass of a grain of sand, at that speed, can release energy, comparable to a small explosive detonation on impact. A pebble could vaporize a ship. Over the course of a multi-year journey covering trillions of kilometers, you're not going to avoid every particle in your path, you're going to plow directly through a stream of them. Then there's radiation, Cosmic rays, high-energy particles flung out by supernovae, and other violent events saturate the galaxy. On Earth, we're shielded by our atmosphere and magnetic field without even thinking about it. In deep space, none of that protection exists. A multi-year crewed voyage means a crew soaking in a radiation dose that, over time, becomes lethal without heavy shielding. And heavy shielding means more mass, which loops us right back to the energy problem from Section 3. Every solution to one barrier makes another barrier worse. That's what makes this a trap, not just a challenge. This is usually where someone in the comments says, "Fine, relativistic rockets are hard, so what about shortcuts? Wormholes? Warp drives?" Worth addressing head-on, because it's not crazy science fiction. These ideas come from real solutions to Einstein's equations. A wormhole is, in principle, a tunnel connecting two distant points in space-time. The math allows it. The catch is that keeping one open and stable requires something called negative energy density matter, with genuinely bizarre properties that we've never observed existing in any usable quantity. Even optimistic physicists treat this as not ruled out, rather than plausible. Warp drives the idea of contracting space ahead of a ship and expanding it behind, so the ship itself never breaks. The light speed limit locally have a similar problem. The 1994 proposal that kicked off serious warp drive research required exotic negative energy matter in quantities that, depending on the model, range from more than exists on Earth to more than exists in the observable universe. So the honest answer is, exotic shortcuts aren't proven impossible, but they currently require ingredients that may not exist in nature at all, in quantities that dwarf anything a civilization could plausibly gather. Betting the future of interstellar travel on wormholes is a bit like planning a road trip that requires you to first invent a new law of physics. Which brings us back to the question that started this. If the galaxy is 13 billion years old, and it only takes a few million years to colonize a galaxy at sublight speed with self-replicating colony ships, where is everybody? This is the Fermi Paradox, and the usual answers are dramatic. Maybe intelligent life is freakishly rare. Maybe civilizations always destroy themselves. Maybe they're hiding from us on purpose. But there's a quieter, more physics-grounded answer sitting underneath all of it. Maybe nobody's missing. Maybe they're all still home, not because they lack ambition, but because the bill for leaving is simply too large for any civilization to pay, not in dollars, but in energy, in time, in acceptable risk. A single failed antimatter-fueled colony mission could be an economic and human catastrophe on a scale no government would sign off on twice. If that's true, it reframes everything. It means the galaxy might be quietly full of civilizations, each one glued to its own solar system, each one running into the exact same wall we're running into, not an empty universe. A crowded but sealed 1 trillions of isolated rooms in the same enormous house, none of them able to open the door between them. Here's the reframe I promised at the start. If interstellar travel really is this hard for everyone, that also means the scary version of this story. An aggressive alien empire sweeping through the galaxy, conquering star systems, is almost certainly off the table. Building an interstellar armada runs into the exact same energy wall as building an interstellar embassy. The math doesn't care about your intentions. And it means the path forward for us isn't necessarily starships. It's listening. A radio signal, unlike a spacecraft, travels at the actual speed of light, with no fuel, no life support, and no risk. If there's someone out there within a few hundred light years, a conversation, even one with decades-long pauses between sentences, is still within reach. We might never shake hands with another civilization, but we might eventually hear one. And honestly, finding out we're not alone, even from a message that takes 40 years to arrive, would still be the single biggest discovery in the history of our species. So the next time someone asks, if aliens exist, why haven't they visited? You now know the real answer isn't they don't exist. It's that the universe was never built to be easy to cross. Light speed is a wall, energy is a wall, time is a wall, and empty space itself, moving fast enough, becomes a wall too. If this kind of deep dive is your thing, hit subscribe. I break down one mind-bending physics question like this every week, and drop a comment. If you could send one message to another civilization, light years away, not knowing if you'd ever hear back, what would you say? See you in the next one.